Hello everybody, myself Harismita Reddy.S and I'm back again with another presentation on this topic on the subject of data structure applications. And today the topic will be synthesis of hardware models in C with pointers and complex data structures. Now the content of this presentation is first of all the introduction and the methodology and related works, background and under background. We have three topics: memory representation, pointer analysis, definition of the subset, and in the fourth topic we have mapping to hardware. Under this we have memory refinement, pointers, resolution of malloc and free, and in the fifth topic, library of allocations and optimizations, we have optimized general purpose allocator, specific purpose allocator, implementation and results. In this we have tool flow and experimental results of and discussion, and finally the conclusion. Now let's get started. The C language was originally designed to develop the Unix operating system. It provides uh, it provides constructs to directly access memory and to manage memory and input-output using the standard C library. These constructs are widely used in software. Nevertheless, many of the networking and multimedia applications implemented in hardware or mixed hardware-software systems are also using complex data structures stored in one or multiple memory banks. As a result, many of the C or C++ features that were originally designed for software applications are now making their way into hardware. Dynamic memory allocation is tightly coupled with pointers and notion of a single continuous address space. Pointer differences as well as memory allocation are all referring to the main memory. Now, coming to the first topic, we have methodology and related works. Now, basically, in hardware, memory bandwidth is often a bottleneck in applications such as networking, signal processing, graphics, and encryption. At the architectural level, after partitioning, the system typically consists of multiple communicating processes to be mapped to hardware or software. Memory segments are defined for internal storage or shared memory. These memory segments can then be mapped to one or multiple memories during synthesis. Some of the storage area, for example, are internal variables, can be statistically allocated during synthesis or compilation. In software, memory allocation and deallocation are implemented as primitives that are part of the operating system. Memory management can also be implemented in hardware. For memory allocation and deallocation, instead of the system calls to the OS, requests are sent through signals to an allocator block, also known as the virtual memory manager, which is implemented in hardware. Background. In hardware at the behavioral level, designers want to have control on where data are stored and want to optimize the locality of the storage. Typically, the chip design contains multiple memory banks, register files, registers, and wires. To efficiently map C code onto hardware, the storage space must be partitioned. During synthesis, each partition is then mapped to a register, a wire, or a memory. Some of these partitions may also represent pointers. Memory representation. The simplest memory representation consists of a single address space in which all data are stored. This trivial representation, however, prevents optimizing the locality and parallelizing the code. On the other hand, the most accurate presentation, which would distinguish each element of arrays or of recursive data structures, is not practical. As a result, most analysis techniques combine elements within a single data structure. Pointer analysis. Pointer analysis is a compiler technique to identify at compile time the potential values of the pointers in the program. This information is used to determine the set of locations to which the pointer may point. For synthesis, in the case of load, stores, and free, we want to synthesize the logic to access, modify, or deallocate the location referenced by the pointer. For this purpose, the point to information must be safe and accurate. Safe because we have to consider all locations the pointer may be referenced, and accurate because the smaller the point, points to set S, the fewer logic circuits we have to generate. Definition of the subset. In this section, we only talk about restrictions on the synthesizable subset. Limitations on the generated architecture may also exist, akin to the limitations of the behavioral synthesis tool used as a back-end to our tool. In particular, the techniques presented here do not depend on the type of memories. Now, in the fourth topic, we have mapping to hardware. In mapping to hardware, we have memory refinement. After analysis, the storage in the program can be represented as a set of distinct location sets. This set of location sets represents a partitioning of the memory. Each location set is ultimately mapped to a wire, a register, or a section of memory in the final design, as shown in the figure. Pointers. In hardware, as discussed in section 3, data may be stored in multiple registers, memories, or even wires, for example, output of a function block. Therefore, to efficiently map C code into hardware, pointers may not only address data in memory but may also reference registers, wires, or ports. Pointers can be used to allocate, read, write, and deallocate data. Allocation and deallocation performed through the standard library functions malloc and free are dealt with in the next section. Resolution of malloc and free. In software, malloc and free are implemented as standard library functions. Similarly, for hardware synthesis, we use a library of hardware components implementing malloc and free. The idea here is to have one component called allocator implementing both the malloc and free functions as introduced in section 2. In order to efficiently manage memory, we want to support multiple customized memory allocators that may allocate storage in multiple memories in parallel. As a result, we partition the memory space in which data are dynamically allocated into a set of memory segments. Library of allocators and optimizations. Optimized general purpose allocator. General purpose allocators are defined as allocators that may allocate blocks of various sizes. These allocators consist of the circuit that performs allocation or deallocation and two lists that keep track of the free blocks and the allocated blocks inside of the memory segment. Specific purpose allocator. The malloc function takes one argument, the size of the block to be allocated. When this size is a unique constant, k for the malloc, calls mapped one memory segment. This memory segment can then be represented as an array of elements of size k. Optimizing sequences of malloc and free calls. Some dynamic memory allocations are sometimes not necessary and can be automatically remained. This is especially true for legacy code in which malloc or free are used to manually control storage. Implementation and results. Tool flow. Under tool flow, several tools can be used in this methodology. For memory management at the system level, tools are used to help in refining data structures and defining a memory architecture. Coming to experimental results and discussions, these two tables will give insight of the results and the discussions of the experiments. Conclusion. So in this presentation, we have presented how C code with pointers and malloc or free can be efficiently mapped to hardware. Thank you for staying with me till the end, and I hope you found this presentation informative.